everybody, welcome back to our third screencast for our notes for our circular motion unit. This one's going to focus on centripetal force. Now, according to Newton's second law of motion, we know that net force, F net, is equal to the mass of the object times its acceleration. All right. Well, we learned in a previous screencast that an object that's moving in a circle has acceleration because it is changing its direction constantly, which means changing velocity. Well, hopefully we appreciate that objects that have acceleration must also have an unbalanced force or a net force acting on them. All right. So that means that net force is our centripetal force in this case, and that will be equal to the mass of the object times its centripetal acceleration. So please note the C's indicating we are moving in a circle. All right. Now, when an object moves in a circle, we call that net force this centripetal force. All right. And that force, just like our acceleration, always points in the same direction. All right. So that means that we are going to be pointing our force values to the center of the circle, just like we do our acceleration, which makes sense because it is called centripetal force. So center seeking force. All right. And just like with acceleration, this force is going to be in the well, this is written badly, but it'll be perpendicular. Oh, I just spelled that wrong. Sorry about that. Perpendicular direction to the velocity. So let's say to the velocity. All right, so what does that mean? All right, so we got our tennis ball here. Let's put a tennis ball in a little further along the road here. All right, the velocity for our tennis ball is still going to be tangent to that circular path. All right, so here's our velocity value. All right, but just like we saw with our acceleration, the acceleration and the force both will point towards the center of our circle, which make them both perpendicular to that velocity value. All right. So centripetal acceleration or force, both center seeking, both are going to point towards the center of the circle. And you can see that as you move around this circle, so let's say the tennis ball later is in this position, all right, that our velocity will now be moving in this direction, and our acceleration and force values will be pointing in a different direction than they were before. All right, so the direction that your acceleration and force point is always to the center, but that may not always be the same. Sometimes it may be up, sometimes it may be down, sometimes it could be to the left, sometimes it could be to the right. It depends on where you are in your circular path. Okay? Now, this centripetal force is a very general term. So Fc equals F net. And it's not a new force. It's not like we're adding to our list of forces. All right? This Fc is caused by other forces. So in other words, depending on what you're talking about, maybe gravity is what's pulling it to the center. So let's say you're spinning something up into the air. When it's at the top, the force pulling down on it is going to be due to gravity. All right, maybe it's the normal force. All right, we're going to talk about Ferris wheels and other rides, loop the loops, and it depends on which way your car is facing, but maybe it's the support that's pointing towards the center. All right, we also could have a frictional force that's causing the centripetal force. Cars going around curves stay on the curve because of the friction between the tires and the road. All right. And then just like friction, we could also have air resistance if something's moving in a circular path but in the air. All right. And then finally, just like our tennis ball, we could have a string attached. Someone standing in the center of a circle, a string attached to a tennis ball, they spin it over their heads. It's the tension force between that string and the ball that causes that centripetal or center facing force and acceleration. So we're going to see in problems that we work later, when we want to identify that centripetal force, it's going to be one of these that we've already talked about. So I just don't want you to think centripetal force is a brand new force. No, it's just a general name for one of the forces we already know that's pointing to the center of a circle. All right, so let's try a couple problems. All right, for the first one, we have a 65 kilogram person riding a roller coaster. The roller coaster has a loop with a radius of 15 meters and goes through this loop with a velocity of 20 meters per second. All right. So what is the centripetal acceleration of the person as they go through the loop? All right. So we know the mass is 65 kilograms. All right. We know the radius of the loop is 15 meters. And we know the speed or velocity is 20 meters per second. All right. So for centripetal acceleration, that's going to be equal to mass. Oops. Sorry, I did that wrong. That's going to be equal to velocity squared divided by the radius. All right, so we know both of those numbers, so we're going to plug those in. 20 meters per second squared divided by 15 meters. Plug that into our calculator, and we'll have an acceleration value of 26.7 meters per second squared. So that's the acceleration that is pointing towards the center of the loop. Well, the next question is, well, then what is the centripetal force that's acting on this person as they go through the loop? Well, we know that centripetal force is equal to mass times that centripetal acceleration. And now we have both of those numbers as well. So that centripetal force is going to be equal to 65 kilograms times 26.7 meters per second squared. All right, if we multiply those together, we're going to find that a force of 1,733 newtons is acting on this person as they move through the loop. All right, now we used force equals mass times acceleration, but I should mention that sometimes you aren't given acceleration directly or asked to find it. So another way to think about this formula is we could plug in what we know for that acceleration. So you could rewrite this as the centripetal force is mass times v squared over r, where this v squared over r is equal to that centripetal acceleration. So it's a second formula that comes in pretty handy. All right, now for number 2, a boat with a mass of 7,500 kilograms is traveling at a speed of 45 meters per second. When the boat turns, there's a centripetal force of 12,000 newtons acting on the boat. All right, so what do we know? We have a mass of 7,500 kilograms. We have a velocity of 45 meters per second, and we have a centripetal force of 12,000 newtons. All right, so the first question is, well, what is the net force acting on the boat? All right, well, the net force is that centripetal force. So it is the FC, all right, which means that is 12,000 newtons. All right, so what's causing this centripetal force? All right, well, if you're in a boat, just like in a car, when you turn the wheel, it turns fins on the boat or the motor, depending on what type of boat you have, and that leads to some friction buildup between the motor, the fins, and the water. So what's causing the force here is friction. All right, and because we're moving through a liquid, we could call this drag, just like we would in the air, or air resistance, but water resistance. All right, now to calculate the centripetal acceleration, we're just going to use our formula, v squared over r. But then I go and look and I'm like, oh no, I don't know r, so I can't do this. All right, so instead I'm going to use my formula for centripetal force, which is mass times acceleration, and I know my force and my mass. So I plug in 12,000 newtons for that force, 7,500 kilograms for the mass, and then my unknown is the acceleration. I divide both sides by 7,500, and I find that the boat is accelerating at 1.6 meters per second squared. All right. And then last, what is the radius of that turn? So again, I know that acceleration can be v squared over r. And this time I know the acceleration, I know the velocity. So I'm going to be able to use this formula, but solve it for r. So I plug in 1.6 meters per second squared is equal to 45 meters per second squared divided by our radius value. I swap the radius and the acceleration values, and I find that the radius of this particular turn is 1,266 meters. Wow, that's a really big circle, but that's okay. Okay, so again, centripetal force has to be there because we have acceleration. still center facing, just like the name suggests, and you can solve it in one of two ways. If you know the mass and the acceleration, the centripetal acceleration, you can use Newton's second law, force equals mass times acceleration. If you don't know the acceleration, but you know the velocity and the radius of your circle, you can substitute those values in for the acceleration and solve that way. Okay? Our next screencast is going to look at drawing force diagrams of objects in circular motion, but you're going to need all of this information. So make sure you've gone through these screencasts or have your notes completed before moving on to the next one.